Hey guys, it's Tom Cherryums with the FujiNet project, and I wanted to kind of go ahead and make, hopefully not too long a video here showing some of the things that I'm doing while I'm waiting for the FujiNet hardware to prototype to show up here. And one of those things that's very important is I'm having to take and modify or add functionality for Coleco Atom to the Z88 DK compiler. Thanks to the wonderful work at the Z88DK team, I was able to take and present my findings based on reading the EOS programmer's manual and a few handful of other technical manuals, present all of that in a whole series of notes, and was able to take and send that over to the Z88DK people. And they were able to take and make the first pass of the bindings, which I will take and start refining, and I'm actually refining. So with that, we'll just kind of do kind of a run through of one of the applications that I'm doing as a test program, which is a simple sector copier for tapes called QCopy. The code for this is up on GitHub, so you can take and check it out there as well. For my bootstrapping process, I'm actually using an Atom Net Drive emulator. So, I mean, you can see that guy here. Let me turn on my secondary camera here so you can see. I'm using this excellent piece of hardware right here. Whoa, wrong direction! Which is Arduino based, but it's enough to get running because it has an SD card slot and allows me to take and bring software over here until we get the FujiNet running. It plugs up via USB for power, but it also plugs up to the Atom Net here. The Atom Net is basically an RJ12 connector that's reversed on both ends. So, basically telco order. So with that, we can take and do a little run through of this program here, which will take and copy a disk image that I will take and select right here. I'm just going to pick, I'll pick Atom Calc, sure, why not? Click, select it into drive 1, and so that is device 4, and device 8 is the tape drive number 1 over here. Now this, if you haven't seen one of these interesting little contraptions before, this is one of the Atom tape drives that is a part of the Atom memory console. And yes, your eyes are playing tricks on you, because this is indeed, it does indeed look like a standard cassette shell. It almost is. Main difference, if you look here, there have been 2 holes drilled on the back side to go into retaining pins that are actually on the top of the unit right here. Barely see them. And one of the interesting things that you'll see with the tape transport down here is that the head and the capstan, all of the transport assembly is in constant contact with the tape, but also the tape transport wheels, both tape transport wheels are actually active all the time and actually have some weight behind them. There's a significant motor behind both of these, providing for very high-speed tape access. I'm actually amazed that this exists. One of the other aspects too are these tight springs, which very tightly push the tape up against the transport and make sure that everything contacts quite nicely. Now, for whatever reason, this particular tape transport here doesn't line up exactly okay. You kind of have to be a little weird with it, but push it in. Once it's there, close it, and she's ready to go. So we're going to go ahead and do a little sector copy here so you can see this goofy thing in action. Go ahead. We're going to read 32 blocks from the Atom Net Drive emulator, and then it's going to write that 32 blocks to the tape transport here, and repeat until all 256 blocks have been written to the tape. One of the interesting things that happens is that the tape drive actually has two main speeds. That is, the tape drive is either in search or in read-write mode. In search mode, the tape drive is operating at 80 inches per second, and in read-write mode, the tape drive is operating at 20 inches per second. Now, for those of you who are familiar with how fast tape drives usually go, usually no more than a couple of inches per second, this is very fast. Well, you can see once it finishes writing the block, it stops the tape transport. Now, so you'll notice right there that the tape transport actually sped up a little bit. And that is literally because it had to take and rewind a little bit to find the servo marker for the block, check and make sure it was okay, synchronize up to it, and then do the actual write. This actually contributes to the overall seek speed. You'll notice that the Atom memory drive, the digital data pack drive, does not have any transport controls whatsoever. There are none. The entire transport control is controlled entirely by the microcontroller that is on the tape drive unit itself, and that microcontroller is under the direction of the Z80 microprocessor. You'll see here that we've now gone to block 40, and because this is what they call a center formatted tape, it's actually taking and winding over to the other side here to start writing on block 40. This is what's called a center formatted tape. That is, that block 0 starts in the center of the tape, and thus block 1 is right after it. And this is, and this continues until block 3F. This is honestly so that the directory for data tapes can be quickly found. There is one other format that's actually in use on the Coleco Atom, and that is what's called a write directory tape. And that is that the directory begins at the very beginning of the tape. Block 0 begins at the beginning of the tape, and all of the blocks are labeled essentially sequentially, with 256 being on the other side of the on the opposite end, on the opposite spool. So you might be asking, can you take and convert one tape into another? Not with the drive itself. The DDP drives themselves cannot format the tapes. You can modify them to format the tapes, but as they come shipped from the factory, they do not have the capacity to do so. So what you typically have to do is you have to modify a donor tape, put that tape into a standard cassette deck, dual cassette deck for example, and dub the resulting tape onto a fresh new tape. At which point you can take and then drill the necessary holes and use the tape in the Atom like you saw here. So to really bring that point home, the order of the sectors on the tape, or that is what I would normally call the servo track, is pre-formatted at the factory, so to speak. So if you lose that servo track for whatever reason, the tape has to be redone. You'll see we're now about to write to 80, so we have to take and reposition the tape. One of the interesting things that I see here is that it seems the microcontroller for the tape is very much aware of, it's aware of where it is on the tape. It's constantly searching and seeking for where the servo track is on the tape, and thus what block is passing over the head, and it adjusts the velocity of the motors to take and match, which is a very nice feature and something that's very surprising to find in a personal computer like this. Honestly, these are things that you would find in 9-track tape drives and the like. So we're on block 160 or so, so we're nearing the home stretch for this. It'll be a few more moments before this is completed, and then we'll take and test the tape once it's finished writing. Because we're not recording at 60 frames per second here, and we have this LED on here, we seem to have a bit of a strobe effect with the tape here. But hopefully this is enough to show that the tape is moving pretty darn fast, even when it's writing data. Now, mind you, I've done this over and over and over again over the last couple of days to this same tape. The overall mechanism itself seems to be pretty durable. With that said, it is possible to really jam a tape up by going too fast. These tapes were never meant to move this fast. So what can happen, lots of different things can happen over time. The tapes can come off the spool. You can literally have you can have the individual transport rollers inside the shell basically grind into the casing. You know, all sorts of interesting things can happen there. With that said, I'm actually, again, I'm amazed that this exists and that it works. I'd really like to know who made these, actually. I see references to Honeywell, but I'm not sure that Honeywell were the ones that made it. Maybe Honeywell were the people that were contracted to service them. Yep, almost done here. I'd like to thank William Hicks for making and sending me these tapes. He provides a very valuable service to Atom community members. For software, providing the Atom archive, providing repair services, definitely something you should check out. Now that we're done writing, the tape transport completely stops. And with that, I'm going to go ahead and just stop this right here. Boom. We'll go ahead and stop. Move back over here, and I realized that the microphone was all the way over here. Oops. Darn it. I just can't get a break to get all this stuff together. But with that, we'll take and continue. Hopefully this isn't too bad. So there we go, a functional sector copy program. And as we can see here, it's implemented in just very few lines of code, really. We have just enough to take and write out the banners, to do things like update the block status display, putting things on the correct position on the screen, giving status messages, and doing the tape operations, making sure that we catch errors and the like. And right now I'm using the Z88DK conio.h functions. I may actually take and write an equivalent set of functions that just use the EOS. I'm not sure. I'm going to see what's possible and what's feasible here. There may be a better way to do that. So you can see the main part of the program is really pretty simple. We clear out our buffer, which our buffer is basically 32 blocks of 1024, so 32 kilobytes approximately. I arranged it like this so that it would be very easy to take and pass into the tape functions. C allows you to do that quite nicely without having to do very many acrobatics. And we go ahead and do a little check device here, which basically just queries the device, gets the status information, and if for whatever reason we get an error, then we take and send a retry message to try again until it succeeds. At which point, copying from device, we take and do tape operations for reading, then writing, reading, and writing, doing this no more than 8 times to get all 256 blocks, and then we're done. Right now, the EOS routines are in a very prototypical state, the bindings that is. I'm using a function called ASMCall, which was added into Z88DK a couple of years ago, and based on Konami Man's code to make it easy to call assembly language routines in a manner similar to Int86 and Int86X on MS-DOS platforms, where you basically can set the registers as you want them, pass in a program counter and the register structures and which registers you wish to care about, and ASMCall will take care of ferrying everything over appropriately and ferrying back the results while simultaneously preserving the appropriate stack context and everything so that the program won't go off the rails. We can then take and reference, because we're passing in the same structure for both input and output register values, we can then take and reference it immediately for the return values to use as error checking, for example. Read block, write block, request status, etc. The next step for this, honestly, is to take and basically convert all this to straight assembler so that it can be packaged up with the Z88DK library tool and turned into a proper function library. The advantage there is that all of these functions will not get, only the functions that will be needed by a particular program will be taken and compiled in by the compiler as a result. So we saw this program in action. There's one more that basically shows off rendering something that looks like smart keys using a Mode 2 display here. And I've since taken this and put this into its own little library here, but we see it here in its prototypical form. We'll go ahead and boot this up so you can see it. I will take and reset. And we will go to Atom Smart Keys Test. And you can see the result here. This is what the FujiNet configuration program could potentially look like. It's a quick rendering, a quick render here, but I was concentrating on the bottom here, trying to make something that would look correct for outputting smart keys. There are some things I want to add, such as proportional font output, but for the most part, I've proven that this works and that it works pretty well. If we look, actually, you'll see that the Roman numerals here are actually being rendered 1 pixel at a time. Yes, this will be replaced, but I was just trying to get this accurate. The routine that does all the painting is Smart Keys Adders and takes care of using helper functions here to take and fill parts of the script, fill parts of attribute memory. And then we do small touch-ups with vpoke poke individual bytes into attribute memory, fix up the keycaps, everything's good to go. And finally, we bust out some test data here, some test content. So you can see when it's all said and done, it's going to be very easy to use. And in fact, if we actually go over to, I was going to use it for Atom QCopy, and then I found that I didn't really need to use it, but I had broken everything out into smartkeys.c, where we see much the same code, but I had exposed publicly a single function that would basically spit out the 6 individual legends for you automatically. So, I mean, there we go. That's pretty much it for right now. I'm going to go ahead and leave the video here as it is. I hope you guys have enjoyed this. I'm still working feverishly as hard as I can to try and get things up and running so that by the time that I get the hardware from Oswald, I can start working on the firmware side of things and start working on the configuration program for FujiNet in earnest. So until next time, guys, have fun.